Hi there and welcome back to Calculus of Variations. In this video we're going to derive the equations of motion of a simple object falling under the force of gravity. So let's imagine we have our object here and it's being pulled down to Earth. Okay, and we have a coordinate system here. That's our value of our y, and that's our value of our x. Then we know from Newton's laws that the force equals the mass times acceleration. Okay, so the mass in this instance here we'll call m. Okay, and the acceleration is acceleration due to gravity. Now we can write the acceleration in terms of y double dot. Okay, so the second differential of position is the acceleration, and that's equal to, well, it's the mass, and acceleration is acceleration due to gravity, g, and because of the coordinate system we've chosen, that's going to be a minus. Okay, now that's one equation there. Now the other one is in the x direction. We'll have a mass times acceleration in the x direction. Well, that's going to be equal to 0 because we're only looking at one direction. Okay, so those are our two equations of motion, and what we want to be able to do is we want to be able to derive those using the calculus of variations. Now we're going to use something called a Lagrangian. Now this form of motion here ensures that the difference between the potential, the kinetic energy kinetic, minus the potential energy is stationary. Okay, now that in itself is a quite important thing, and we're going to go back to that at some point in time. You know, you usually see that written as L equals, and for the kinetic energy you'll see it written as T minus V. Okay, now that there is called the Lagrangian, and as I say, I've only just mentioned it here just so we can go through this example to see the power of calculus of variations. We'll go back to this in future videos, and there'll be a lot of work to cover in this. Okay, we're only really just introducing it and touching the surface here. So what we could do is we could write this Lagrangian. So L would equal, now kinetic energy would be about half mv squared, so that's m, and it's the velocity, which is the rate of change of position, x squared, okay, plus the rate of change of the position, rate of change of the position, y squared, okay, minus the potential energy. The potential energy is mass times gravity times the height. Well, the height in this instance is given by our coordinates y. Okay, so we want to be able to use this and the Euler-Lagrange. Okay, so now we could write this here, and we could work out our partial L by partial y minus d by dt of partial L upon partial y derivative. Okay, now we're working out the Lagrangian with respect to y. Okay, so that's going to equal, and we're just differentiating this here. So if we differentiate this with respect to y, the only factor in here that has got a y term is this here. Okay, we're not interested in the y derivative, only in the y term. So this is going to be, m and g is just acts like a constant, so that would be minus m times g. Okay, and this would be minus d by dt of, now it's partial L by partial y derivative. Okay, so what we're going to have here is the only function of y derivative is this one here, so that would be 2 times y derivative times a half m. Okay, so the 2 and the half cancel out, so you would just end up with a value of m y derivative. Okay, so this line here is going to then end up as minus mg minus, and we just differentiate that again with respect to time, so you're going to end up with m y double dot. Okay, and that there equals 0, because we're setting the Lagrangian, we're setting the Euler-Lagrange equation to 0. Okay, so we're going to end up with a value of minus m y double dot equals mg. If we take our minus sign across, we'll have a m y double dot equals minus mg, which is one of the equations that we're looking for. Okay, so that's us got number 1. Okay, so that's us found number 1. Now we can get number 2 by doing the same thing, only with respect to x. So we have partial L by partial x minus d by dt of partial L upon partial x derivative. Now that's going to equal, and let's bring this back up so we can see it. So we're looking to differentiate that with respect to x. Okay, now there is no x term in it. There's an x derivative, but there's no value of x in it, so the first term is going to be 0. Okay, and we're going to differentiate d by dt of the partial L by partial x derivative. Okay, well there's x derivative there, and again same thing, going to have 2 is going to come out, so it's going to be 2x derivative, 2 cancels with the half and you've got left with your m, so you're going to end up just with a m x dot. Okay, so when you differentiate that again, you're going to end up with 0 minus mx double dot equals 0, so mx double dot equals 0, so that's us got number 2. Okay, now another couple of things just to note, and again we'll be getting back to these in detail in later videos, but if we were to write out the functional for our Lagrangian, so we'd have I equals the integral, and we'd be integrating with respect to time from t0 to some time t1 of our Lagrangian L by dt. Now that there will be stationary, okay, and that is called Hamilton's principle. Okay, again we'll go back to that, very important and very interesting, and we'll go back to it in future videos. Okay, also, so really that principle really says that an object will travel in a path such that the Lagrangian is stationary. Okay, that's telling us. Now, if the force is conservative, okay, for example force of gravity, then we can simplify that Hamilton's principle and we can write down something called the principle of least action. So we know that L equals T minus V, and we know that for a conservative force that T plus V, and that is the potential energy plus the kinetic energy, is some constant K. Okay, so then we can write V equals K minus T, so then we could say minus V equals T minus K. So then we can put that into here and we could say L equals T plus, and for the minus V we have T minus K, so that's T minus K. So we could say that our value I equals the integral from, well, T plus T to T, so it's going to be 2 times T, T is the kinetic energy. Okay, now the minus K is just the constant of integration, so we'll leave that out for now, and again we'll go back to that later. Okay, so that by dt, and that says that there is the principle of least action. Okay, that's principle of least action. Okay, now just mention these just as a taste of what's to come ahead. Okay, thank you for listening, and I'll catch you on the next video.